Hi everyone and welcome to the ICTS string seminar. So today we are very happy to have Sourav Roychowdhury from Chennai Mathematical Institute, who will tell us about Non-Abelian T-dual of Klebanov-Tseytlin background and its Penrose limits. So please, Sourav, take it away.
Okay. So first, I would like to thank the ICTS string community to give me opportunity to present my work to you people. It's a great pleasure to me. So here is the title of my talk, the Non-Abelian T-dual of Klebanov-Tseytlin background and its Penrose limit. The work has been carried out recently with my collaboration with my advisor. His name is written here, and the talk will be based on this following paper. Okay. So first, I would talk about introduction and motivation of our work, followed by the technical details, and then I will enter the core part of our work, and then finally I will conclude. Then I will talk about some some future directions, and finally I will conclude. Okay. Yes, ma'am. Okay. So why the planar spacetime, the PPO spacetime important? Important means important in the general relativity as well as in the string theory picture. Okay. So first, the main features of the planar background is it admits a null killing vector and all curvature invariant whatever you can construct for the PPO background, like Riemann scalar or up to derivative from Riemann. So whatever curvature invariance you can construct from the background is identically vanishes. Now, as we know from the string theory picture, from the worksheet formulations of the string theory, we know that all alpha prime correction terms accompanied by the curvature invariance, and just as I told, the all curvature invariance for the PQS vanishes, so it provides an exact string background. And that is the beauty of the planar as far as the string theory picture is concerned. So it provides the exact string background because we know only there are some few solutions provides the exact string background. The beauty of the PQS is provide an exact string background. Okay. Now, if you consider the Polyakov action, which is the starting point for the string theory, and if you consider the Polyakov action for the string theory background, it exactly solvable. And not only that, it is actually just very simple. If you consider the PQA, if you consider the Polyakov action for the PQA background, so it just give you the Klebanov equation for the massive scalar field, as far as the bosonic structure of the full string background is concerned. Okay. Now, from the gauge theory perspective, one can construct the interstring string state via the IDSTFT correspondence. Okay. Now, there is a precise correspondence between the string walk in the PQA background to the set of operators in the boundary gauge theory. Means, if you consider the closed string and if you quantize the closed string in the PQA background, it will give you certain mode. And this mode is actually one-to-one correspondence with the set of operators of its boundary gauge theory. I will make this sentence precise by the next statement. Okay. So now means the ADS-50 correspondence in the context of the PQA background is you have a PQS in the gravity side, and if you are considering closed string quantization on the PQA background. Now quantization means it will give you some certain mode, and this mode is actually one-to-one correspondence by the set of operators in the dual gauge theory. This seminal work is actually this operator has a large arc symmetry charge and associated a U1 symmetry charge of its global string. This work is actually carried out by this seminal work is actually carried out by the three people with name Bernstein, Mallasena, and Napsase in 2002, and they showed actually in their work they showed the ADS-TFT correspondence how it works for the PPS phenomenon. Okay. Now, after BMN in 2002, after BMN introduced the PPA picture, and then over the decades, people have studied this PPA, BMN in type 2B compact applications, for the maximal supersymmetric case, this work is actually carried out by the BMN, and then people as a follow-up, people examine the PPA BMN as a follow-up work with some least supersymmetric background, like Klebanov-Tseytlin background, and the fractional brane background, and so forth. Okay. Now, very recently, not very recently actually, in 2010, actually people turn on interest to examine the PPA BMN in type 2A background. This type 2A background is actually abelian and the non-abelian T-dual of those type 2A backgrounds. Those type 2A backgrounds is actually quite well known in the context of the PPA and BMN picture. Okay. So now, as we know from the work by the Buscher in 1990 and follow-up work by the Hassan, how to construct the abelian T-dual background means if you consider if your background admits some U1 isometry, U1 global isometry, then we know how to construct is by applying the procedure of the Buscher and the follow-up work by Hassan, how to construct is equivalent type 2A background. Okay. So now, very nicely, non-abelian T-duality is actually the generalization of the Buscher rule for the non-abelian background. Means if you have a background which admits some non-abelian isometry, the simple case is S2, then one can generalize the idea of the Buscher and the work of the Hassan, one can construct its T-dual background. Okay. So nicely one can say that non-abelian T-duality is actually generalization of the abelian T-duality where the dualized group is non-abelian, like S2. Okay. However, there are some certain differences if you compare some non-abelian T-duality to its abelian counterpart. There is actually some many differences. So, first of all, as we know that abelian T-duality is actually abelian T-duality is a symmetry of the full string background. However, the non-abelian T-duality is actually not a symmetry of the full string background. It's only valid for its low energy excitation. Means if you consider just the supergravity limit, it behaves well. Okay. So now the so far understanding is non-abelian T-duality is just a solution generating technique as far as the low energy excitation is concerned. Means the supergravity. Okay. Now now the question one can obviously ask: it is not a symmetry of the full string background, then why we will take care about the non-abelian duality? Okay. This answer is, although it is not a symmetry of the full string background, however, it is a beautiful solution generating technique for the low energy excitation. So, so means one can construct new supergravity background by applying non-abelian T-duality from the known one. And interestingly, this new background means after the dualization with the resultant background is actually new boundary safety. This is quite different from its original boundary safety. Okay. Now the question, the group of people in Swansea University, the question they actually asked, although that, as I mentioned, the non-abelian T-duality doesn't provide any, it is not a symmetry of the full string background, but does this non-abelian T-dual background provide any exact string theory background or not? Means this non-abelian T-dual geometry provides any PPA or not by considering the Penrose expansion that I will come later. Okay. And they actually in a paper in 2018, they showed that non-abelian T-dual of ADS site S site means S site is actually there is a SC in the S site which exhibits some SU2 isometry, and they considered the non-abelian dual of this background and they examined the BMN and PPA. Okay. So motivated by their work for the ADS site case, so me and my advisor in our previous work, we actually we went one step further. One step further means actually we considered the non-abelian T-dual of Klebanov-Tseytlin background, which is actually the least supersymmetric background, n equal to 1 supersymmetry, and we examined that PPA BMN in the T-dual background, and we also got the PPA geometry. Okay. Now, as we know, this starting from the ADS side, then Klebanov-Tseytlin. There is some, so this is actually kind of series of backgrounds. Series of backgrounds means we know that there is a RG flow starting from the Klebanov-Tseytlin fixed point, and then the next background is Klebanov-Tseytlin, and it's end up with the Klebanov-Tseytlin. Not only that, this background is kind of interesting in the sense they are actually the least supersymmetry. They are like n equal to 1 supersymmetry. So this background is, so we can say this is kind of towards the realistic model. Okay. Now the group of people is already worked out is T-dual background, means non-abelian T-dual background. So this all like Klebanov-Tseytlin, Klebanov-Tseytlin, and Stadler, all non-abelian T-dual solutions are available. So now the question what we ask in this literature that we have already got the PPA in the non-abelian T-dual of Klebanov-Tseytlin background. So similarly, can we get for the Tseytlin case, this non-abelian T-dual background provides any exacting background, means they provide any PPF solution or not. That we examine in the present literature. Okay. So here is the outline of my talk. First, I talk about some technical details. I will not go through the entire detailed calculation. I will not go through that. I will just briefly mention what about the non-abelian T-duality, what is it, and then I will talk about the Penrose limit. After that, I will enter the core part of our literature. These two are the core part of the literature. First, I will talk about the type 2B compactification and its non-abelian dual, and then I will show the examination of the Penrose limit in the non-abelian T-dual of the Klebanov-Tseytlin background. And if time permits, I will talk about the dual field theory. Although the dual field theory is not quite understandable, the dual field theory mostly I will talk about the original and the dual background, and I will speculate some comment about the PPF limit, dual theory for the PPF limit, and finally I will conclude and make some comment about our ongoing work and future direction. Okay. So non-abelian T-duality. So just I mentioned very beginning that non-abelian T-duality is actually the generalization of the abelian T-duality, where the group is non-abelian, like SU. Okay. Just as a quick recap for the Buscher work, the famous Buscher work for the abelian T-duality. Okay. So abelian T-duality is the procedure Buscher rule for the abelian T-duality is actually the 3-step recipe. Okay. What we do for the abelian T? First, we consider some sigma model action, and we start from a background which has some U1 isometry, and we consider the sigma model action on the background. And first, we gauge the U1 isometry. Means we make the global isometry to the local one by introducing the co-derivative and the H field. And then we introduce a curvature term and with the accompanied by the Lagrangian multiplier to invoke the flat function. Then we integrated out the gauge field, means we just ruled out the gauge field from the picture, and we end up with the abelian T-dual model. So this is the 3-step recipe for the abelian T-duality introduced by the Buscher. Okay. So non-abelian T-duality is actually very beginning. Non-abelian T-duality at very beginning it actually goes along the same line if you compare with the abelian counterpart. So here also we consider some sigma model actions, and we get some non-abelian isometry like SU2, and here also we invoke a flat connection by introducing the gauge field and the Lagrangian multiplier. However, here the gauge field is actually the group value. Here is the expression of the gauge field, where TA is actually generator of the corresponding group, like SU2 we have like J, and up to some constant factor. Okay. However, there are some so many differences if you consider with this abelian counterpart. First one, as we know, for the Buscher rule, if you consider like if you start with some U1 isometry, after ending up the abelian T-dual model, we will also have the U1 isometry. So like it's like I map U1 to U1. However, as I will show in our example, that non-abelian T-duality actually doesn't do that. So it does not like some SU2, some SU2 goes to SU2, or some S3 goes to S3. So you can say it just like maps from one supergravity solution to another. Okay. Not only that, the main drawback about the non-abelian T-duality is quite different. This point is actually quite different from its abelian counterpart. So abelian T-duality preserves the U1 isometry. However, the non-abelian T-duality actually destroys the isometry. What does it mean by partially? That I will show in an example. Anyway, so this not only that, that is actually the main. This is actually main the obstruction to consider the non-abelian T-duality as a symmetry of the full string background, because as we know the abelian T-duality, you can go back. Go back means you can start from a background, dualize it, and again if you dualize it, you will go back to the initial point. However, for the non-abelian case, the isometry is actually destroyed, so you can't go back to its original model. However, this isometry can be recovered as a non-local isometry in the resultant sigma model and the corresponding sigma model, because means the original sigma model and the dual sigma model is actually canonically equivalent. So in the language of there is actually another way to study about the non-abelian T-duality is known as the double field theory. In that context, actually the non-abelian T-duality is actually this two sigma model, this original and the dual sigma model, is can be shown is actually the Denfeld domain. Okay. So there I mentioned for this reason about the symmetry has been lost. So non-abelian T-duality is not a full symmetry of the genus perturbation theory. So we don't even know how to proceed the non-abelian T-duality about the GS prime expansion. However, there are some recipes about the alpha prime issue, which I talk about at the very end of my talk. Okay. So now the thing which I should mention, apart from the solution genetic technique, it turns out that if you consider like in an abelian T-dual of ADS5 S5, which gives a type 2A supergravity solution, and if you consider the M lift of this solution is actually resemble to the GM geometry. Okay. So now these people, actually the Swansea people with their like so many literatures, more than 15 or 20 literature, they investigate the non-abelian T-dual, got the various type 2 backgrounds starting from ADS5 S5, ADS4 S7, or ADS. Yes?
Can I just interrupt? I'm a bit confused by the statement that there is an ADS5 cos S5 type 2A supergravity solution. What is
No, the non-abelian T-dual of ADS5 S5.
Okay, so what is the type 2A supergravity solution that you get?
So Lava, actually I'll come to an example. That time you will get. Not about the ADS. Okay, so ADS5 S5 means S5 can be written as a S2 some fibration over S3, right? Now, okay, so just let me say S1. So now S3 supports an SU2 isometry. Okay.
Okay, and then you're kind of
so actually
in the worksheet.
So when you talk about the dualization of S3, we will get to some like figure geometry.
Okay.
So, but I will talk about an example with ADS3 SP4. That time is actually quite simple example you can follow. That actually the next slide.
Okay.
That's slow. Shall I proceed? Okay.
Yeah. Okay.
Yeah. Okay. So now these people actually with their number of literatures, they consider various type 2 backgrounds like ADS5 S5, ADS5 T11, ADS4 S7, like so many backgrounds, and they construct the non-abelian T-dual solution of those type 2 backgrounds. And with they actually in their literature, this is in their literature they describe the technical details, they fixing all their issues in order to carry out the dual solution. However, for time being, I am not going to their detailed technical details about the construction of the solution. However, I will show you one example. So in order to just complete the picture about the non-abelian duality, I'll considering the example by the ADS-CST. So I'm considering the example about the near horizon geometry of the undefined system. And as we know, the near horizon geometry is described by the ADS-CST T4. And the NS sector, we have a matrix given by the ADS-3 part and the S3 part and the T4 part. And RS sector, we have a S3. Okay. So now S3 indicates we have a global isometry. It's a four global isometry which can be decomposed by some SU2 left into SU2 right. And the Swansea people in their literature, they consider the SU2 left and they construct the T-dual solution. Yeah. So here is the T-dual solution for the ADS-CST T4 case. And you can see that ADS-C will remain as ADS-C in the dual solution and the T4 will remain T4. However, the S3 actually gives some non-trivial part. This is actually the dualization of the S3. Okay. Now there are some interesting features about the solution. So let me go one by one. Okay. So now, if you consider some small limits, this geometry is actually RC. Okay. First of all, what I mentioned, apparently you can see that we start from like S3, which is actually quite compactly compact manifold. However, in the non-abelian T-duality, this one non-compact direction has opened up. In nicely, we can say there is a non-compact direction. However, it is not quite non-compact that you will see. Okay. So now, if you consider the smaller limit, this geometry is effectively RC. However, if you consider the larger limit, the geometry is R cross S2. So we can say the non-abelian T-duality is actually interpolates between RC. If you consider the S3 dualization, it actually interpolates between RC and R cross S2. Not only that, the main interesting feature is if you consider the larger limit, the geometry is R cross S2. Now, if you compactify R, means if you identify the R with some coordinate psi, this solution is actually end up with the, interestingly, this solution is actually end up with the abelian T-dual solution, because if you consider the S3 and abelian T-duality act on the fiber. Okay. So means at a larger limit, abelian T-duality and the non-abelian T-duality behave same. So when you talk about the dual field theory, is actually larger limit, the dual field theory for the non-abelian one is actually the n copies, where the n is very large, of the abelian one. Okay. So now, however, this is actually valid as for only for.
Can I just ask a simple question? Maybe I missed it. So the point is that this is a transformation from type 2b solutions to type 2a Subra solutions, type 2b.
Yes.
To type 2a Subra. Is that
yeah.
the general statement?
Yeah, it is okay. So I will come to that. First of all, it is what I am showing is I am going type 2b to type 2a
at a Subra level.
At Subra level.
And this is a general statement that you always generate a type 2a Subra solution this way?
Thanks, Loga. You asked this question. Then I also mentioned. Okay. So here, Loga, I am actually dualizing of S3, right?
Sorry, come again.
Yeah. So here I am dualizing S3. S3 means SU2.
Okay.
So now is depend the chirality change or not that you are asking. It's actually depend number of generators. Like if you start with like odd generators, if your number of generators is odd, like for S3 we have 3 generators, then we will end up with different chirality.
Okay.
However, However, if you just consider the generators, even number of generators, like any modular space or in like coset space, there actually the number of generators is actually even depending on the group. So in that case, you end up with the same chirality.
Okay. But here you're saying you go to massive type 2A. So there is, I mean, there's some. So But this is a general map that that you always go to massive type 2A?
No. It depends. Actually, no, it can't. Because if in original solution, it depends the fluxes of your original solution. If
Okay.
your original solution admits F3, like ADS3, S3, T4 admits F3, so you have then F0. This is the mass in the type 2A.
Okay.
But if you consider the ADS5, S5, you have only F5 in our sector.
Okay.
So in dual sector, you end up with F2 and F4.
Okay. Can I just ask one more question and then I'll leave? So I mean, so this is supposed to be some symmetry which acts also at the level of D branes and so on, like which, like, for example, usual Abelian T-duality maps D branes to D branes, right? It wraps I mean, there's some rule of how to map D branes to D branes. But and also, you know, like it acts at the level of DBA action itself, right? I mean, so is there a statement like that for this?
Actually, these are actually like open direction about the non-Abelian T-duality. So
Okay.
if you talk about D-brane picture, it is better to talk about in the field theory level, right? And actually, this is like quite, there is, you can't make some general statement how the like dp goes to dp plus 2 or dp goes to dp plus 1. You can't make statement about the, as far as the non-Abelian is concerned. There is no like general map. You have to work out like the fluxes, and the fluxes how the D-branes couple, that statement you can make.
Okay, thank you.
Actually, that's why actually people talk about.
I mean, if you know how the flux is transformed, the Raman flux,
exactly,
you work backwards and see how it acts on the D-branes.
Yeah. So that up to, so only from the Raman fluxes you can make you can talk about the D-brane picture.
Yeah, but so there should be a definite answer, right? I mean, if you start with some D-brane system, what it would become?
So like okay, that's actually I am not quite familiar about the D-brane picture. But actually, you have to work out by solution. Any sub like DP how the under duality how DP maps that. I don't have any clear picture about that.
But you are saying that there is a clear picture on how it acts on the Raman fluxes, right?
So for like some Raman flux, you can like how the like you have a like F2, so there is some D6 contributions like that.
Yeah, but so suppose you have a DP, then it produces some Raman fields.
Yeah.
Then you can see how that transforms, and then work backward to see how what kind of D-brane it produces that flux, right?
Yeah. Yeah.
Okay, thank you.
Shall I proceed?
Yeah, fine.
Yeah. Okay, thank you. Okay. So now in other sector in the T-dual background, so the inner sector of the T-dual background, supposed by dilaton and the two forms, and the other sector is actually we have all fluxes. All fluxes means F0, F2, and F2. However, I think it will show that I mentioned the non-Abelian T-duality actually partially destroys some symmetry. You can see, just let me go to the previous slide once more. So this S3 is actually some S2L, S2N, and I dualize about the S2L. So S2 in the dual solution, S2L is actually completely destroyed. However, the residual S2R is actually the reflection here. This is actually the reflection of the SU2R, which is actually still present in the dual solution. So this one is actually partially destroyed the symmetry. Okay. So now, interestingly, this T-dual background provides some massive type 2A supergravity solution because the F0 is present here. It can be identified as a Roman mass. Okay. So this complete the non-Abelian T-dual section about in my work, and I showed a voltaic example, which is a DSP SPT4. So is there any more question?
Yeah, sorry, one more question. Is this always true that the non-abelian T-duality at some asymptotic limit can be thought of as abelian T-duality? Because
yes,
it can always be? Is the answer yes?
it can always.
Okay.
Asymptotic limit is actually gives some asymptotic limit, it gives some abelian T-dual solution. But only lower, but only for NS sector. But RF sector is not like that. Because it's different.
Sorry, this I'm trying to understand. It only so for NS sector it becomes abelian T-duality, but it does not act as abelian T-duality on RR sector at asymptotia. I mean,
no, what I say, so you have a non-abelian T-dual solution as well as the abelian T-dual solution. Okay. So now, if you consider the asymptotic limit, like say r tends to infinity, your NS sector of non-abelian dual will match with the NS sector of the abelian dual.
But the RR sector won't. Is that I'm trying to understand why? So this doesn't respect supersymmetry or something. Is that?
Okay, then supersymmetry. Then I should make one comment as we mentioned. So naively, the supersymmetry of the dual background is preserved if your dualized direction doesn't coincide with the spinor direction of the original background, filling spinor direction. Then your supersymmetry will be preserved. Like for the Klebanov-Tseytlin background, the supersymmetry is preserved in the T-dual solution. However, for the ADS background, which is n equal to 4 supersymmetry, however, after dualization, we will end up with n equal to 2 supersymmetry.
Okay. Okay.
And the another comment I should make that the RF sector is actually completely different. Different in the sense, if you consider the ADS side, if you consider the abelian dual, it will give you only F4. But in non-abelian case, you will get F4 as well as F2. It's completely different solution for the as far as if you consider the RF sector.
Yeah, I guess like whether you get from you mean from F3 you get F2 or F4 depends on how the direction of T-duality like is aligned with respect to the indices where the fluxes are turned on, right?
Exactly.
I mean, in general, you will get both, right? I mean, if kind of.
And here example like F3 has a leg around S3 direction, right? Yeah.
Okay. I mean, in the sense that if you take the F3 hat and or F3 and then you kind of T-dualize it just in the usual way. So I'm wondering what would you get? Would you get this F0 F2 F4? Can I understand this F0 F2 F4 just from this asymptotic limit, or is it
no? Asymptotic limit you can't get the asymptotic limit is only valid for the NS sector. RF sector you can't match from the asymptotic limit if you compare it with abelian counterpart.
Okay.
Okay. So now actually I will talk about Penrose limit. What is Penrose limit? So Penrose limit is actually associated to every space-time metric or a line element. So means and the choice of a null geodesic. In that we will explain, and that the space-time is actually a planar metric if you consider the limiting extension. So means you start from a background. The background means you have a metric or line element. And if your background admits some null geodesic, which is actually I am parameterizing by the gamma, and what we do actually we expand the background metric around the null geodesic. Means we actually zoom in the background around the null geodesic. Okay. So means we start from a background which admits some null geodesic, and we zoom in the background around the null geodesic. Okay. So now first consider the geodesic equation. For that, first consider the geodesic equation. Here is the geodesic equation, and U is actually some affine parameter. And I am considering a motion of a particle with very high speed, and the motion is going to take place some isometric direction, let's say A. Now, if you consider the motion of a particle along some isometric direction with no acceleration, and there is no motion along other directions, the geodesic equation actually boils down to this expression. And if you break this, if you write down this expression explicitly, and by implying the condition that I am going to consider motion along a isometric direction, the geodesic equation is actually boiled down here. So whenever I talk in future, whenever I talk about the geodesic condition, means I am talking about this condition. Together with, just as I mentioned, the particle is moving with very high speed, so it follows the null geodesic condition. So this is the null geodesic condition. Okay. So now actually I am entering the core part of our work. Okay. So as we know, in 1997, Johann Malvicena introduced famous ADS-CFT duality, by which shows some equivalence pictures, the stringy nature of the ADS by S side to the boundary CFT4 dual, which is n equal to 4 supersymmetry. Okay. So after Malvicena introduced the famous ADS-CFT duality, people were trying to examine what are the gravitational dual for the other 4-dimensional CFT. And the next work is actually carried out by Klebanov and Tseytlin in 1999. So they considered the ND3 band placed at the conical singularity, which gives rise some SUN times SUN is large n gas theory, which is n equal to 1 supersymmetry. And the gravitational background is ADS5 T11, but this is the metric of the T11 part. Okay, sorry. Now, as you can see, the T11 is actually admits some more cycles, which is the conductible loop and the cycles. So together with the regular D3 band, one can consider the wrap band, which actually the wrap this cycle means the fractional band. And this work is actually carried out by Klebanov and Tseytlin. They consider with then regular D3 band, they consider the wrap D5 band, which is actually the fractional D3 band, which wrap the cycle. And this geometry is actually SUN plus m with SUN gas theory, with n is very large. However, due to the presence of the fractional band, this background is no longer conformal. It is not a conformal background. However, the background is n equal to 1 supersymmetry. Okay. And the geometry of this, and the geometry is given by the following metric, where this is the Minkowski part. And interestingly, the geometry carried a wrap factor, which is contained by a logarithmic term. And this log factor is also present in the transverse Calabi-Yau space, as well as the Minkowski part. And the wrap factor is actually contained by the logarithmic factor. So this actually is a singular background. You can see from the wrap factor. Okay. So now this background, okay. So just let me put some more remarks. So if you compare the Klebanov-Tseytlin background with Klebanov-Tseytlin background, there are some certain differences. Differences means in nanostructure, this background carries a two form, this non-zero Klebanov form, which is given by here. And due to the presence of the fractional D3 band or the wrap D5 band, we have F3 contribution. And this is the F3 contribution. And the regular band is there for the regular band. We have a usual F5 contribution. This is the F5 contribution. And these are the some wrap factors, the TR, PR, and KR. This factor actually can be fixed if you consider the type series supergravity equation of motion. And it turns out that this P is actually number of the D3 band present in the background. This is actually kind of measure of the number of the fractional band. Okay. Now, if you consider the Killing algebra, the Killing vector algebra of this type series background, it can be shown that it supports an SU2 isometry. Now, the Swansea table is actually consider this Klebanov-Tseytlin background, and they dualize along the SU2 isometry. Yeah. So this is the T-dual background for the Klebanov-Tseytlin case, and the background is quite complicated. However, the things which I want to emphasize that the Minkowski part is actually behave the spectacular part. It is also present in the T-dual space. However, the radial directions and the 1s2 is also preserved in the T-dual space, and there is actually three-dimensional. This actually there's some three-dimensional space that I will actually present in the next slide. However, this is the wrap factor here in the background, which actually refers the wrap factor by introducing some parameter or tilde, which is take over the two constant factors in the original the wrap factor, and A is given by this expression. However, the DS3 is actually generated by the T-dual coordinates, the V2 and V3, and psi is actually the T-dual coordinates, and it has some complicated form, and this is the DS square 3. However, the thing which I want to mention here, although this looks quite complicated background, however, you can see from here, this background actually enables some one isometry along one azimuthal direction, which is phi 1, and here you can see the background has also an isometry along psi direction, which is actually hidden here. Okay. So now this background admits some, this background actually supported by the Klebanov and the dilaton in the NS sector, and our sector we have all flux like F0, F2, and F4. So it is also a massive type 2A background. Okay. Not only that, this so this is actually a massive type 2A supergravity background, and this background actually preserves the supersymmetry of the original background. Okay. So is there any question? Okay. So now what I am trying to do is actually we consider the two isometric directions which I presented earlier, the psi and phi 1, and we consider the motion of a particle along psi direction as well as phi direction. Okay. First, consider the metric component along the psi and phi 1 direction. So this one is the metric component along psi direction, and this one is the metric component of the phi 1 direction. Okay. So now first consider the psi direction, and if you impose the geodesic condition means the del mu g psi psi 0, it gives some singular value. So if you hit like g psi psi, this gives some, if you hit the geodesic condition here, it will give some r equal to r tilde and v equal to 0. So for this the metric component itself vanishes. So it gives some singular contribution. So for that, we didn't consider the psi direction, we didn't proceed further. The psi direction, we want to another direction, another symmetric direction, which is phi 1 direction. And by imposing the geodesic condition, we end up with some non-singular values given by theta 1 equal to pi by 2 and v2 equal to v3 equal to 0. All other values leads to the singular contribution, which it doesn't consider. Okay. Now, as I mentioned, apart from the geodesic condition, we also make sure the geodesic is null. So in order to do so, first we consider some expansion. First we consider the geodesic some r equal to constant, which is not a tilde or 0 because these two are singular. And we expand around some xi is equal to 0, means the mean process part, and we expand around v2 equal to v3 equal to 0 that we got from previous geodesic condition. Okay. However, it turns out that this geodesic doesn't lead to any PPF geometry. Okay. So now what we consider, we left this direction, but we consider now the motion of a particle with non-zero angular momentum. Means now we are going to consider the motion in a plane which is governed by the r phi 1 plane, and obviously as the motion is taking in a plane, so it carries some non-zero angular momentum. Okay. So now we expand we consider the geodesic given by the xi is equal to 0 and theta 1 equal to pi by 2 and v2 v3 equal to 0, which we got from here, and we propose the expansion is the following way. Here we rescale the v2 and v3 coordinates. Okay. And together we propose the expansion here, and subsequently we took the L tends to infinity limit. Okay. So now the next job is to work out the coefficient Ci, the 6 coefficient Ci that we have to work out. Okay. So now if we impose the null geodesic condition, the out of 6 coefficient, the 3 can be fixed from the null geodesic condition given by C1, C2, and C4. And After the extension, there is some order of some divergent terms of order of L that can be actually eliminated and it turns out that the Cc and C5 they are not independent, so they are actually related by the following expression. J is what J is the angular momentum. However, you can see that this coefficient Ci is actually the singular coefficient because there is some singularity r equal to r tilde. This is actually the signature of the singularity of the original background, which is still present at the Penrose moment. Okay. So now, in order to normalize, so now there we have also fixed the C6 term here, and that can be fixed by considering the usual normalization of the light cone term in the plane wave metric. So that can fix the coefficient C6. Okay. So after the expansion, we can see the metric is given by here, and there is no like order of L term and order of L plus term. So kind of there is no diverging term in the order of L, and this is the metric of the expansion where the coordinates is there are 10 coordinates u, v, y, w, z, v2 psi, v3. These are the 10 coordinates. Okay, but still there is one thing is missing to fix C3 and C4. However, it turns out that the background is actually supported the V2 and phi in the NS sector, and our sector we have a F2 and F4. The F0 contribution at Penrose limit is actually vanishes. Okay. However, as we know, talk about the plane wave metric, is it easy to if we replace it is easy if we represent the metric in the Bridgman form, and however the metric we have got here is not in the Bridgman form. So in order to express the Bridgman form, we consider the deformation which is along the transverse coordinate as well as the one light cone coordinate by this following fashion, and then the metric end up with the Bridgman metric, and this is actually the form of the plane wave metric in the Bridgman representation. And you can see if you consider the waveform means sum u equal to constant surface. So this term will go away, this term will go away. So this waveform, the metric will end up with some Ri. So means the metric is means the waveform is actually the plane. Okay. So now we can consider so if I is the expression given by the here, and if we put back this coordinate transformation, we will end up, this is actually the Bridgman form of our metric, and you can see this Fi is known as the Bridgman mass, and the singularity is actually the presence in the original form is actually hidden in the Bridgman mass form. Okay. Okay. So now as we represent the metric, so now we have to talk about cases.
Hello, maybe I'm just asking a question. I mean, what is the physical significance of all these log R's? I mean, like, why do you get all these logarithmic terms? I mean,
so actually, I'm not taking the logarithmic term. It comes from the. So they all actually comes from the Dirac factor. So okay, so let me go there. So this is the original Chapter compactification.
Okay.
The feature carries as a logarithmic factor.
Okay. And
so this, yes.
And this R0 gets replaced by, I mean, yeah. So now, so here you have a log.
Yeah.
And then you're saying that after you do this non-abelian T-duality, you get logs in many places. Is that?
Yeah. So actually, the log is also present in the non-abelian solution here.
Right. That's what I'm trying to understand. Okay. So okay. Can I rephrase this question? Like, can you write this metric in terms of some particular kind of D-branes or something? Is that you know?
Like,
can you write it in terms of from H and H inverse, like the thing that you started with before the non-abelian T-duality?
Okay, that actually I have to look out. Yeah, it's a good question. That actually leads to some event picture. Yeah.
Yeah, I just want to ask physically what is happening. Like, what are the new d branes and what are the like fluxes in the new solution? And if you can just
So from the given perspective, okay, that actually I have to look. But is it possible to write in some H and H inverse from that?
but you have some physical interpretation for this final solution that you get after the non-Abelian T-dual.
So because you have some like F0, F2, and F4 fluxes.
Okay. Mm-hmm.
From that actually we have some like D6, D2, and D4 contribution.
Okay.
But yeah,
but you know the geometry of these things. How if you think about them in terms of the d branes, how the d branes
that
they
actually
intersect or they
possible to write like some HR or HR inverse, or if you consider some asymptotic limit event that is you will able to write it or not, that actually I'm not quite sure about that.
Yeah. Yeah, it's just that it's very complicated and I'm not able to see through what is happening. But okay, that's okay. Okay.
It's actually so that's why actually people say that it's just some like solution generating technique. So you will start some solution, you will generate some supersymmetric solution. Yeah.
And it doesn't worry you that all these logs are inside square roots. Like the logs can go negative and the thing can become complex.
So actually, I'm considering only that like r greater than r tilde or r greater than r naught. So only that space I'm considering.
But what happens at r equal to r tilde? The space closes off.
So that is the singularity.
Come again. That is the
singular point, that r equal to r tilde or r equal to r naught.
Oh. So there's a curvature singularity in r equal to r tilde.
Yeah.
And that singularity is naked or is it covered by some horizon? Or?
It's a naked singularity.
It is a naked singularity.
Yeah.
Okay.
And that is actually main point, that this singularity is present in the original solution, and still this is the present in the T-dual solution as well as the Penrose limit. So this PPOF is actually kind of singular PPOF.
Okay, I'm not sure I said, but okay.
Okay. So now we presented the T-dual metric. We present the PPOF in the Bigman form, and now here the background fields at the PPOF limit. So these are the background fields in terms of the Bigman representation, and you can see from here this is quite complicated form. However, the thing which I want to emphasize is that if you consider the expression of the H3, it has a leg along U direction, which makes sure the H3 actually is a null flux. And we know from the construction, the Blau construction of the PPOF, that at Penrose limit, all the fluxes has to be null. And it also reflects in the RS sector that I mentioned earlier, that F0 is equal to 0 at Penrose limit. However, that these are the F2 and F4 in the Bigman representation, and it has a leg along U direction, which makes sure that these fluxes are also null. Okay. Since the background fluxes at the Penrose limit is or null, and we have explicitly checked in our literature the type 2A Bianchi identity, and the gauge field equation is satisfied for the PPOF background that we got here. It means that our PPOF is actually the solution of a type 2A supergravity. Okay. So, but still there is one thing is missing to make comments about C3 and C5. So in order to do that, we consider the Einstein equations for the type 2A supergravity, and these are the Einstein equations. Actually, there are two equations for the type 2A supergravity. And if you consider the second equation, the R is 0 that I talked at very beginning for the PPOF, that R equal to 0, and the fluxes are the null flux. So first and last term will vanish. However, we have explicitly checked this term and this term, and it turns out that they are separately gone away. So second expression actually doesn't give any non-trivial contribution. So we lift it up. So then we consider the first one, and we know that only non-trivial contribution comes from the, if you consider the big man P2F in the big man representation, that only non-trivial contribution comes from RUU component. And this is the Einstein equation for the RUU component. And if you represent the P2F in the big man form, RUU is actually the du square term, the trace of the du square term given by here. And if you calculate the H square UU, this is actually involves the unknown coefficient here, C5. So in order to make comment about C5, if you consider the Einstein equation, so this leads to make the form of the C5. Okay, so this actually completes my the geometric structure. So okay, so how much time I have?
You have about 5 minutes, but how much time do you need?
Actually, some 8-10 minutes or so.
Yeah, this should be fine.
Yeah. Okay.
Please go on.
Okay. So now actually I will talk about the field theory. Although the field theory is not quite understandable for the non-abelian T-dual sector, although the people make some comments about the non-abelian T-dual sector, which I am trying to present now. Okay. First of all, as I mentioned, that the Klebanov-Tseytlin background is actually a singular background. Okay. Now the field theory dual of the background is actually consists some non-conformal due to the presence of the rat band. The background is non-conformal, and which is actually n equal to 1 supersymmetric with SUN plus 1, SUN guess theory, which actually n is very large. And it actually describes the dynamics of n regular DC bands along with m fractional DC bands placed as a conical singularity. Okay. So this is actually kind of in one sentence. This is actually kind of different pictures in original background. Okay. Now for the non-abelian T-dual geometry, if we talk about the dual theory of it in the construction, it's actually based on the domain wall configuration. Means we will compare the domain wall in the original theory and what can be the domain wall in the T-dual theory. That actually these people describe in their literature. Okay. So now in original background, one can form the domain wall can form by a D5 band, which is actually extended along some R12 direction of the main cosy part, and is actually wrapped the compact direction by θ2, phi2, and psi, which actually we consider for the dualization. Okay. So now one can consider the dynamics of low energy excitation are captured. So now one can consider the low energy the bond end actions of the D5 well volume, and actually this gives rise to some corresponding effective tension. This actually okay. So now as I mentioned, this non-abelian T-duality is actually performed along SU2 isometry. So then wrap D5 actually end up with some D2 which is extending along R12 of the dualized geometry. One can carry out the same thing with the same bond in field actions and we end up some effective tension. However, it turns out that the two effective tensions before and after dualization is matched up to a constant factor. Okay, so this actually doesn't give any new message about the dual theory of the non-abelian background. Okay. Now one can carry out the holographic central charge and entangled entropy by RC formalism, and this also match up some RG independent coefficients. So examining the bond and field actions and the holographic central charge entangled entropy doesn't give any new insight about the dual theory of the non-abelian one. Okay. However, there is one strange thing that people notice that if you consider the gauge coupling analysis of the field theory perspective, it behaves for the non-abelian one, it behaves some logarithmic to the power 3/2, which is quite mysterious behavior or quite unknown behavior, because in original KT theory it behaves like it behaves some log, but in the dual theory it actually behaves logarithmic to the power 3/2. This behavior is quite mysterious, and this is so one can infer that the non-abelian, the dual theory for the non-abelian one is not a, maybe it's not a 4-dimensional theory, or it is not actually conventional field theory which we familiar. Okay. So now in the original setup, this original background, we have a D3 and D5, and the T-dual background, we have a D6 and D8. So it admits, the original background admits some cycles, as well as in the T-dual background, if you fix some coordinates, we will end up some 2 cycle or 3 cycles geometry is present in the T-dual background. So one can calculate the Maxwell and phase charges for the various Maxwell and phase charges for those bands in original as well as T-dual background. Now, after calculating the chart, it turns out that the dualization D5 actually goes to D8, and the D3 actually, and twice the number of the D6 bands for each D3. So actually D5 goes to D8, and D3 actually gives 2 D6. Okay. So now actually one can see that fiber duality, which is actually present in the original background, is actually also present in the T-dual background. Here fiber duality means the fiber duality in the geometric picture. Means in original background we have a D3 and we have B2. So one can actually introduce a large gauge transformation of the 2 form B2, and then there's some amount of phase charge is induced in the D3 band. This phase charge, the induced phase charge is same if you do a suitable radial change, in the radial component, and it is same as the Maxwell charge. This is actually kind of geometric picture of the fiber duality present in the original background. Now, these people have showed in their literature that same similar phenomenon is also observed in the T-dual background. But instead of the D3 band, in the T-dual picture, we have a D6 band. And here also, actually, we can have we present the fiber duality by introducing a large gauge transformation on the B2. So one can speculate that the T-dual geometry undergoes to cascade of the fiber dualities much the same way as the gauge theory corresponding to the original theory. However, as I mentioned earlier, this D3 actually gives 2 D6. So one can see that if you apply the fiber duality in the original background, so and if it affects the change of M units in the D3 band chart in the original Klebanov-Tseytlin background, is actually equivalent to the change of 2M units of D6 band chart, change of 2M units in the D6 band chart in the non-abelian background. However, what about the Q1 of the non-abelian T-dual background is still unknown about what is actually the Q bar and how the gauge group behaves along the Q bar is still unknown in the non-abelian T-dual sector. Okay. So now, for the and all actually why it is unknown, all problems is actually comes from the its singular nature. Okay. So now actually one can say that so one can calculate the brane charge at the PPA background, the Maxwell and phase charge for the D6, D8, and D8 brane, and it turns out that it vanishes due to lack of cycles. Okay. So the one speculation one can make, this kind of speculation one can make about the gauge theory dual for the PPA background is actually there is no longer cascading due to the large gauge transformation of the B2, and which is leads to because there is no brane charge present in the PPA at the PPA limit, so there is no longer any cascading due to the large gauge transformation of B2, which leads that actually Q-bar theory or Q-bar theory dual to the PPF geometry means the BMN operators, which is a dual theory for the PPF geometry, is actually sits at the end points of the cascade. Means it is actually sits the conformal point of the cascade. However, there are so many things that are missing still. So as I mentioned from the very beginning, that the idiosyncratic correspondence for the PPF scenario is we have a closing quantization in the PPF sector is give some mode, and this actually one-to-one correspondence with the set of operators in the boundary space. In our literature, we still couldn't identify the BMN operators in the Q-bar gauge theory because the Q-bar theory is itself is missing. Okay, and the correlators of the gauge theory correspondence in the correlation functions of those BMN operators in the gauge theory operators in the gauge theory side is also missing in our literature because we couldn't identify the BMN operator system. So now let me conclude. So we studied the non-abelian T-dual background of the non-abelian T-dual background of KT geometry with respect to some SU2 subgroup. And this non-abelian T-duality is not a symmetry of the full string theory, but it actually provides some new supergravity solution. So it is a solution generating technique in the supergravity level. And we studied actually various null geodesics and one null geodesic and obtained some Penrose limits in the non-abelian background. And the geodesic, which carries actually angular momentum, leads to PPF geometry. And the speculation we made about the PPF limit, that there is no cascading at the PPF limit. So Kuber theory means the BMN operator is which is actually dual to the PPF geometry, is turning the endpoint of the cascade. Okay. However, this further investigation is needed to identify the BMN sectors, means the BMN operators, and the precise mapping. Mapping means mapping to modes to the operators, and the other holographic computed quantities and the field theory observation. Okay. So as a future direction, we are trying to explore the PPF geometries in the non-abelian or full Klebanov-Tseytlin background, as well as posted geometry. And interestingly, we have some deformed supergravity backgrounds like lambda deformation, eta deformation, and as well as background in the ADS-3 spectrum. So actually, in an ongoing work, we consider these together. Together means the lambda deformed background, which is actually which contains the ADS-3 factor, and in an ongoing work, we consider some lambda deformed ADS-3 ST4. So ADS-3 means we actually inhibit some SL2R symmetry, and ST we have a SU2, and the people have already studied the lambda deform of SL2R as well as SU2, and this is the resultant background. And this background is actually supported by B2 and phi in a sector, and our sector we have F1, F3, and F5. But it is quite interesting background because this RF sector is actually purely imaginary. So it is not like a usual supergravity background. It's known as the type 2 star background. The question we are actually trying to address that does this geometry is admit any exacting solutions or not, although it is an imaginary sector for the RF sector, but does it provide any exacting background, admit or not, means it admits the PPF geometry or not, or even if it admits some PPF geometry, so at PPF limits, there still any lambda dependence is present in the background. In the background means in some Bigman mass or any like comp-field at the PPF limits, still there any lambda dependence is present or not. That we are trying to address, and it is very actually in initial stage. Hopefully, we will get some result very soon. Okay. So these are some key references of my work, and these two actually the quite good literature. This is kind of, you can say, this kind of textbook about the non-abelian T-duality. They examine the various type 2 non-abelian T-dual of various type 2 compactifications. And these people in this paper, they actually studied the Penrose limits of PPF in the non-abelian T-dual of ADS5 and S5 background. Okay. So yeah, thanks, and I stop here. And thanks for that.
Okay, thank you, Sourav, for the very nice talk. Are there any more questions for Sourav?
Hello. Yeah. So I had a like somewhat of a basic question about the motivation of this thing. Like, if you take an n equal to 1 supersymmetric theory, what does the Penrose limit teach us? I mean, in the usual, like ADS5 plus S5 BMN limit, there is some protected thing, and you can match something in the field theory with some calculation here. Like even in the Klebanov-Tseytlin solution, I mean, even before non-abelian T-duality, what does the PP wave teach us? I mean, what is the, like, it's not like you expect something to be matched, right, across?
But yeah, as far as only the PPF thing is concerned, so there is, first of all, the PPF provides the exacting background. And there is a precise map to string modes to operators, the BMN operators. Now, as I mentioned, that non-abelian
So
T-dual
this is true even in, sorry, this kind of a map between operators and string states is true even in Klebanov-Tseytlin background.
in original background is okay. So in original Klebanov-Tseytlin background, the PPF actually doesn't. We don't have any PPF in the original Klebanov-Tseytlin background.
Okay.
Yeah. So that actually in one thing which I should mention. Although it original background doesn't admit any PPF geometry, it non-abelian counterpart admits the PPF geometry.
Yeah, but even if you find something, I'm just trying to ask. Let's say I'm as a field theory, as somebody who's interested in duality, what do we learn about the duality by studying this background? With
Yeah, so actually kind of we couldn't identify that dual map, but as far as the gravity set, only the gravity part is concerned that it admits the PPF geometry. And what actually the motivation our things that the non-abelian T-duality doesn't provide any non-abelian T-duality is not a symmetry of the full string background. But the question is, does it provide any exact string background or not? So if you just consider the gravity sector.
okay.
And that actually we showed. People have already showed for the ADS5 S5 case as well as we showed for the Klebanov-Tseytlin case. So there is actual kind of series we are trying to add this. That if you consider just the gravity sector, it admits some PQA solution or not. That is the first actually goal to our work. That was actually first goal to our work, that it admits some PQA geometry or not.
Okay, that is good. But I'm right in saying that say if it admits a TP wave, it's not like I can study the string theory and the states are not protected or something. This doesn't give you some nice quantity to duality invariant quantity to calculate. Am I right in saying that, or
yeah, that actually we couldn't identify in our literature, that we couldn't talk about that map and all these things.
Sorry, I couldn't hear you.
Non-abelian for the gauge theory dual of non-abelian T-dual of Klebanov-Tseytlin case is also not clear about the Q here.
Okay.
So it's actually two steps. If you want to study the dual sector for the PQA, we have to first identify the Q here, and first actually you have to understand first the dual theory itself for the non-abelian case, and then the particular sector of the dual theory.
Right, but I mean, if the sector was protected, you could imagine that you could just calculate the sector and then try to guess the quiver.
Yeah. So if you see,
but it doesn't seem like it is protected, right? I mean, so that is not possible in this thing. Is that right, or am I right, or am I wrong?
You're right, but actually from the map, actually we are not able to make any comments of the gauge theory.
Okay. Thank you.
Any more questions? Yeah, just a small point. What is exactly type 2 star?
Okay, so type 2 star theory is, so it's actually kind of applying abelian T-duality along time direction. So in type 2 star theory means your RF sector is completely imaginary, and it comes out if you have some type 2 solution, and if you are applying T-duality along time direction.
I see. Okay.
Then initially you end up with some type 2 star theory. But it's actually we don't know that it is provide any exacting solution or not. That actually we are trying to address. But yeah, the type 2 star theory is nicely used.
And could you apply non-abelian T-duality along the time direction, like for the full ADS3 piece, for example? It would be non-compact, I guess. I don't know if it's a problem.
Yes. But the non-abelian duality is actually beyond SU2 is actually not quite understandable.
I see. Okay.
Even if you consider like ADS5, S5, and if you consider the dualization of full S5, S5 means you have SOC. That also actually there are some hidden problems. If you go through their literature, you will get there are some singularities issues, all these are there. So before actually go to after SU2 is actually quite not actually quite well how to deal with SU2.
Any other questions? Okay, if not, let's thank Sourav again for the nice talk. So thank you, Sourav.
Yeah, thanks for that.
Yes, I'll end the meeting now. Bye.